Hey guys, how are you? I'm glad you're back with me. Again, this is going to be the chemical equilibrium lecture. What I'm going to try and do is to present everything in the PowerPoint from chemical equilibrium. I will present it in the order that they appear in the new order files. It's listed as -NO for new order. So we'll do sections. I will cut the video and then there'll be another section. I will put all of those in a playlist for you guys so that you can see them, but that way we'll be able to skip around a little bit more. So the first part that we're going to do is the review. And I'm going to go ahead and share my screen so that you guys will be able to see what I'm talking about. So we are in the chemical equilibrium lecture. The first review question we have is consider the reaction of sulfuric acid and barium hydroxide to produce barium sulfate and water. Note that barium sulfate is an insoluble exception to the rule. What are the ions that come from the dissolution of sulfuric acid and barium hydroxide? Okay, so the first question they've asked me is what happens when I put these things in solution? So I have two components that I want to talk about, one of which is the barium hydroxide. Ba is a group 2 alkaline earth metal, so he has a 2+ charge. That means that if I'm going to put him with hydroxide, which is a -1 charge, I need to have 2 of those. Oh, wait, hold on. Sorry. 2 of those. I will be reacting that with sulfuric acid, which is H2SO4. I know that because SO4 is a 2- charge. It's a polyatomic ion that's available. It's in the list of polyatomic ions that you have. If it's a 2-, then I need to add 2 protons to that to make that work. So eventually we're going to be balancing this, but I asked, what ions do I get from this when this goes into solution? So when these things come apart, both of which are ionic, they are going to come apart. I'm going to get a Ba2+ and 2 OH- from that. I'm going to get 2 H+ and an SO4 2-. So those are the ions that I'm going to get out of this particular solution. So that's the first question. Awesome. Let's look at 2. Is reaction between ionic compounds, molecular compounds, or both? Defend your answer. Oh, darn it. I just said they are ionic. Now, something that I want to clarify for you guys. These are both ionic compounds. So BaOH2 is an ionic compound. H2SO4 is an ionic compound. The polyatomic ions that exist in each, OH- and SO4 2-, are molecular compounds that happen to be charged based on the number of electrons that they have. Okay, so technically the answer is both. What I was looking for was that it was ionic because that would recognize that this thing is going to fall apart when it goes into solution and is going to make the Ba2+ and the 2 OH-. The OH- does not come apart because it's a complex polyatomic ion. That stays on its own. We have some reactions that do break them up. I don't like to ask about them, so the polyatomic ions will stay together for you, at least until later, okay? So, is that between ionic compounds, molecular compounds, or both? The answer I was looking for was ionic, and there are molecular components within each, okay? If I consider this, would I expect both products to be soluble? Why or why not? Okay, so I'm going to go back and I'm going to look at this first question. Note that barium sulfate is an insoluble exception to the rule. So if I knew my solubility rules, then I would be able to see that one of them is that most sulfates are soluble, but barium is one of the exceptions to that rule. Now, you will have the solubility rules that are in the exam handouts available to you on the exams. I encourage you to work with them when you're doing homework. But that means that the barium sulfate that is produced is insoluble. Now, it says, what happens if one's not soluble? Well, what does it mean when it's not soluble? What that means is that I'm going to form a precipitate. So I'm going to have solid that falls out of solution and sits on the bottom. Okay, so that's what that's talking about. For the fourth one, what are the balanced ionic, molecular, and net ionic equations related to this reaction? Okay, so there are three types of equations that we can write. One is going to be the molecular. That one will be right there. We can have the ionic, and we can have the net ionic. Now, in our molecular, everything is a molecule. We keep everything together. So that's why we have the BaOH2 and the H2SO4. So that's in the molecular equation. For ionic, we're going to have everything in its ionic form. So any ions that I form. So that would be the Ba2 plus, the 2OH minus, the H2H plus, and the SO4 2 minus. And our net ionic is going to be the stuff that's involved in the interesting chemistry. Now, typically for interesting chemistry, we're either looking at the formation of a solid or the formation of anything that is not in the same phase, i.e. a liquid. Here we have both. Water is a liquid, so that is a different phase for that product. But the net ionic equation that I want is the one for the barium sulfate. So I'm going to start with the ionic equation, and I have a reason for doing that. So I said that barium is an alkaline earth metal. He has a 2+ charge. I have my hydroxide ion. I add to that the H plus and the SO4 2 minus. Now notice this is not what I wrote above, okay? But in my head, when I was writing the thing above, this is what I was thinking about. So if I have a Ba2 plus, I need 2 OH minus to make that neutral, and that's how I get the 2 of them. Now, in this equation, I just put a 2 out in front of the OH minus. When I do it in the molecular equation, I have to include that there are 2 of them, and that becomes a subscript. So the charge on Ba, the 2 plus, becomes the subscript for the OH minus. And the charge on the OH minus becomes the subscript for the Ba. We leave the 1 off. Okay? So that's that. Now, I also know that it's an SO4 2 minus. So because that's 2, I need to have 2 of the H plus to make that balance. And so I have that there. And that matches exactly with what I had written above. Now, on the other side, for my ionic equation, I form an insoluble solid. And that is BaSO4 solid. We write that way because it's not dissolved in solution. So we need to indicate that it is a solid that has fallen out of that particular reaction. We add to that the 2 OH minus, and I never leave myself enough room for all of them, and the 2 H plus. I'm going to leave them that way because I do have OH minus and H plus that exist in solution, even though I have liquid water. I'm going to leave them like that, okay? Now, that's how I get to this BaOH2 plus H2SO4 goes to, and again, I'm going to have a BaSO4 solid plus an H2O. And of course, that's a liquid. So that's my balanced molecular equation. Now, do I have enough of everything? I have 1 Ba and 1 Ba. I have 2 OH. And this is technically an HOH. The OH came from the Ba2 plus. The H comes from the H2SO4. So that's where that comes from. So if that's the case, I need to have 2 OH minus from the Ba2 plus. And that means that I'm then going to put this as 2 H2O. That takes care of the 2 OH that I have on the BaOH2 and the 2 protons that I have on the H2SO4. Okay, so, and I can write it like that when I balance the equation if I choose to. That is perfectly fine. All right, so that's my molecular equation. Now notice, I did the ionic first because I need to know what those charges are to be able to balance the molecular equation. So in order to get those charges right, I need to know what the charge is on each of them. So that's why I do that one first. My net ionic equation is where we're talking about only the quote-unquote interesting chemistry. So since I made a solid, I want to talk about that. Now the other thing, this OH minus that exists here, and this OH minus that exists here as a product, those are exactly the same. That OH has done nothing. It's not involved in anything, at least the way that we've written it. So we're going to eliminate that. It's a spectator ion. It's just standing around watching. Same is true with the H+. Okay, so we'll eliminate both of those. And whatever's left is what I should have in my net ionic equation. So I should have Ba2 plus an SO4 2 minus going to BaSO4 solid. Okay? So those are the three types of equations that we talk about. Sometimes you'll get asked about one of these. It may not be all of them. So you should know the difference between them. So it's important that we know how to do all of those, okay, and how to make sure that they're balanced. Questions, comments, problems. And you'll notice that when I was balancing the molecular, I said that there were 2 BAs on the product or on the reactant side, 2 BAs on the product side. I actually make myself a little sheet. And I leave those polyatomic ions together. But that way I can do, okay, there's 1 BA on the reactant side, there's 1 BA on the product side, there's 2 OH on the reactant side. Initially, I only had 1 OH on the product side. I have 1 SO4 and 1 SO4, and I initially have 2 H plus on the reactant side, and initially only 1 of the H on the product side. So I can multiply that H2O by 2, and then that balances everything out. So that's the little thing that I do to make sure that I've accounted for everything. So anytime I make a change, I cross it out and put the new number, because it doesn't just affect one thing, it affects them both. Okay? Make sure that that count is accurate for, like, if you have oxygen in more than one place, you need to make sure that that's included. Okay? So, next question. What forces would you expect to exist between water and hydroxide ions in this solution? Okay. So let's talk about our forces. We talked about the forces that exist. We will talk about in the review the forces that exist. There are 4 types of forces that we need to be able to deal with. The first of those, the strongest, is hydrogen bonding. The second, down from that, is ion dipole. The third is dipole-dipole. And the fourth is called van der Waals. Now, if you don't remember, van der Waals forces technically exist when all of the electrons on one particular molecule move to one side and all the electrons on another molecule move to the other side, so that they're temporarily attracted to each other. So we're talking about forces in between 2 molecules. So that is a temporary thing, but it happens all the time. So everything will have van der Waals forces. This is always true. We always have van der Waals. Okay. In order to have a dipole-dipole interaction, we need to have a dipole on both molecules. And so let me remind you what an H2O looks like when we draw its Lewis structure. So I have an oxygen, it's bound to a hydrogen, it's bound to a hydrogen. When I count the number of valence electrons that are present to make this happen, I know that oxygen has 6, hydrogen has 1 each, times 2 of them. It gives me a total of 8 electrons. Sorry, times 1. I'm doing so well today. Holy mac. This is times 1, so that gives me 6 there, 2 there, total of 8. Okay, so I have 8 electrons, 4 of which are taken up in the bonds, because we always draw the bonds first. So we subtract those 4, and I know I'm overlaying everything else. That leaves me with 4. Those 4 electrons. Next thing that we do is try to fulfill the octet for anything on the outside. But H is weird, because H can't have an octet and only has room for 2 electrons because he's in the first row. He has 2 that he has access to. Okay, so his duet is full. So we don't put anything on the hydrogens. That means that those 4 electrons that are left get assigned to this oxygen. And we put them on as lone pairs, right? Now, I have drawn that they're all this way in 3-dimensional space. It could, I have 1 here, 1 here, anyway. What that means is that I have a net pull of electrons. So the lone pairs pull those electrons. The other thing is that that oxygen-hydrogen bond is actually not completely covalent. It's polar covalent. So the electrons spend far more time with oxygen than they do with hydrogen because oxygen is more electronegative than hydrogen. So the net electron pull is up towards the oxygen. That means that this molecule has a permanent dipole. Okay, so that's a dipole. Water can have a dipole-dipole interaction with anything else that has a dipole. Okay, so I know that water has a dipole. Let's talk about our oxygen-hydrogen. Remember that this is a -1. So again, we have the oxygen, which has 6. There's one of those. It gives me 6 there. I have hydrogen. There's one of those times the 1. That gives me 1 there. But I also have 1 extra electron from the charge. And so that's 1 there. And that also gives me 8. Okay. I still have the 2 from that bond. That leaves me with 6 that are left. Hydrogen is happy. So all of them go around the oxygen. And this thing has a -1 charge. This has a very similar structure to what we were just talking about, and that means that the electron pull is all in that direction. So there is a dipole on OH- as well. Okay, so I'll label that as a dipole. And since there's a dipole in each of them, I can have and do have dipole-dipole interactions. Ion dipole, I require a dipole from water, which I always have, and I need an ion in solution, which OH- is. So I have an ion dipole interaction as well. When we talk about hydrogen bonding only exists when we have a hydrogen bound to oxygen, nitrogen, and fluorine. Those are the only 3 that can do that. It is bound to an oxygen, so we will have hydrogen bonding going on here too. So all 4 of those forces will exist. Okay. Are you expected to know what those 4 forces are? I don't know that I'm going to ask you what they are other than in the context of, do these things exist here? So similar to this question, would they maybe have the 4 forces? Yeah, maybe not. It depends. I don't think that I'm planning on asking you which ones to make you remember what those 4 forces are, which I would have done in 110. So it's the questions you would see on a test probably would include those forces. Okay, but it is something you need to understand as far as what they are and when they exist. Let's look at 6. Consider the reaction of sulfuric acid, barium hydroxide, to produce barium sulfate in water. 25 milliliters of 0.5 molar sulfuric acid is added to 25 milliliters of 0.05 molar barium hydroxide. Has the solution been neutralized? Obviously, I don't have a lot of space here, so I'm going to do some magic with my cute little thing. And I'm going to highlight this equation. And I'm going to copy that. And I'm going to put that here. So I have it again. And notice I'm leaving myself some space above that. I'll talk about that in just a minute. So I know that this question that I've been asked is based on stoichiometry, that is what this question is about. I'm going to have to do math to convert one of these to moles and see what my situation is with what I'm dealing with, okay? If that's going to be the case, I need to take the information that's in this question and pull it out of that question to put it with this equation that I have. Sorry, it was bugging me. It wasn't clean. So I'm going to take anything that's associated with the BaOH2 and write it above the BaOH2. And I'll put anything that's about the H2SO4 and write it above the H2SO4. So it says 25 milliliters of 0.5 molar H2SO4 is added to 25 milliliters of 0.5 molar barium hydroxide. Has the solution been neutralized? Okay, what does neutralization mean? So when I say neutralized, that's a term we use in acid-base chemistry that indicates we've added the same number of acid moles as base moles. So when those two are exactly equal, then I have neutralized that solution. Okay, and the only only thing that affects the pH is the water itself. Okay, that's what neutralization means. Now, I want to show my work to provide proof that neutralization has been reached. What this means is that I have information about both barium and sulfuric acid, both of them. And I need to know if I have the same number of moles of hydroxide as I do H+. So I have to consider both of them to be able to do that. One of the ways that I can do that is I can say BaOH2, and I'm not ready to do math. Why am I not ready to do math? Because I don't have all the information that I need. One of the things that I need, actually, is a molecular weight. And what I'm going to do is pull up my cute little cheat sheet, because I've already calculated molecular weights 8 billion times, so I don't think that there's any value to me in calculating them still. So I come to this little Lentech molecular weight calculator, and you can see I've already put in BaOH2. I typed it wrong, that's why it doesn't like that, because it can't be capitalized. And that is 171.34. And that's grams per mole. Those are the units on my molecular weights. Now, I don't know which molecular weights I'm going to need. Now, I can look at my question and it will tell me. But one of the things that I've found as I go through life is that inevitably I will write down the two that are asked for here, and the next question is going to need so I'll get another question that will need another one. And I hate that. So I'm going to go ahead and do them all right now. That way I have them. And of course, if I have them, I won't need them. So that's how that works. So the H2SO4 is 98.08 grams per mole. The BaSO4 is 233.39, 233.39, and that's grams per mole as well. And the H2O, and that's 18.02. Awesome. Now I have all of my molecular weights, so I can put this nice little calculator away. That gives me everything that I need. Oh, and you couldn't see what I was writing down, but I wrote them all down underneath because, again, I may or may not need them. I'm going to need the one for the BaOH2. And if I want to do a calculation about that BaOH2, I need to know, okay, fine, I have 25 milliliters of that. I also know its molarity. Now, the volume is one single unit or one single bit. The molarity is moles per liter. So I always start with the 25 because then it goes out in the front by itself, and I'm okay with that. 25 milliliters of BaOH2 over times 0.5 moles of BaOH2 per liter. And of course, I can't do that math in my head. I never do. So I'll do the unit conversion within this. Okay. For any of you who don't know what I'm doing right here, these are called, so there are two things here. One is factor label method. So I include the labels, the units with each of these numbers. That way they cancel out. And if all the units cancel that I don't want, then I should be getting the right answer. The other thing is this train track. Everything above the track gets multiplied. Anything below the track is divided. So I think I've explained that before, but I just want to make sure that you guys know what I'm doing. If I do this calculation, that'll tell me how many moles of BaOH2 I have. I don't really care about the BaOH2. What I care about is the OH minus. So I know that 1 mole of BaOH2 contains 2 moles of OH minus. And so I can calculate the number of moles of OH minus that I'm looking at. And I'm over here, I have an Excel spreadsheet because that's how I do my math. 25, 5. And I get 0.025 moles of OH minus. Okay, awesome. So now I know how many moles of OH minus I have. Now I need to know how many moles of H plus I have. So I can set up really the exact same calculation. 25 mils of H2SO4, which is the same thing. I have 0.5 moles of H2SO4 per liter. 1 liter is 1,000 milliliters. And 1 mole H2SO4 contains 2 mole of H plus. And that gives me 0.025 mole of H plus. So I have the exact same number of moles of each thing. So I know that this is neutralized because I have that. Since 0.025 mole H plus equals 0.025 mole OH minus, that's neutral. Okay? So it says, show your work to provide proof. And that's what I'm looking for. I'm looking for a limiting reagent calculation. So you have to show me that neither one of these limits how much is there. Because if one of them was limited, if one was smaller than the other, then I'd still have some stuff left. And I'd have to calculate based on that. Okay, so it's important that we see what our limiting reagent is. Limiting reagent calculations are required if I'm given information about both species. Now, if I were to give you this problem and say, okay, an excess of BaOH2 is mixed with 25 mils of 0.5 molar H2SO4, then I don't have to worry about how much OH minus is there because I've got plenty. Okay, that's what the excess means. All right, so that's how I know that this is a limiting reagent question, and then I need to deal with that. Consider that reaction again. How many moles of protons are present in the sulfuric acid? I already calculated that. That's 0.025. Okay. How many moles of hydroxide? 0.025. How many particles of hydroxide are present? Oh, okay. So here's where the fun stuff comes. I have 0.025 moles of hydroxide. I calculated that. And I know that 1 mole contains 6.022 times 10 to the 23rd particles. In this case, ions of OH minus. I hate it when I draw it like that. That's okay. And so I'm going to take that 0.025 and multiply that times 6.022 times 10 to the 23rd, and that gives me 1.51. Technically, I don't have that many left. It should be 1.5, and I say that because 25 milliliters is 2 significant digits. That means that I should be left with 2 significant digits when I do this calculation. So it's 1.5 times 10 to the 22 particles. Okay, that is multiplying by Avogadro's number. Avogadro's number is available on the test. That value is there. It's not labeled as Avogadro's number, so you need to know what it is, but it is available to you on the exam handouts. Okay. All right, which solution, the sulfuric acid or the barium hydroxide, would have a greater effect on the freezing point of the water solution, and why? Okay, let's talk about freezing point. We want to remember about freezing point depression. We talked about freezing point depression in 110. We know that freezing point depression is described by this relationship. Delta TF is equal to I KF little m, which is molality. Okay, different than molarity, molality. Okay, I know that because that's on my exam handouts, so I remember that equation. Now, the KF is the same because we're talking about water for both of them. So KF is the same. The molality of both of these is going to be the same. I haven't calculated what it is, but I know it's the same because I have the same number of moles of both things, so it's going to be the same. I. What is I again? So I is actually called a Van Hoff factor. And what it stands for is how many particles I get when this thing dissolves. How many pieces does it come apart to be? So my BaOH2, we already said, comes apart to make that Ba2 plus and the 2OH minus. So its I is 3. The H2SO4, its I is also 3 because you get 2 protons and 1 sulfate. And so that's also 3. So would either one of these be any better? And the answer is no. Okay, they would both have the same effect. And that's because both of them have the same I, the KF is the same for both of them, and the molality is the same for both of them. So there's no greater effect from either one of these that we know. All right? So that's 10. Let's look at 11. In the final solution, what is the concentration of the sulfate ions that would be present if the entire solution were dissolved? What is the concentration of the sulfate ions if the entire solution were dissolved? Okay. I'm guessing that this is going to be another one of those places where I need to use this equation. So I'm going to copy it again. Actually, wait, can I do this? Yes, awesome. Sorry, I forgot that this is a new feature and I forgot that it was there. So when we're talking about this, I'm going to use that same equation. I'm going to have my BaOH2 plus H2SO4 going to that BaSO4 plus 2H2O. And I calculated that this gives me 0.025 moles of BaOH2, Ba2 plus, and OH minus. Okay, so if we were to consider the ionic compound together, then it would be the same concentration for that. Oh, wait, that's not true. Hold on. So what I'm thinking about, when we did this calculation, and we had 2 moles of OH minus and 2 moles of H plus, then the Ba is going to be half of that. All right, so we don't do the multiplication by 2 when that happens. And that gives me 0.0125. Let me okay, all of those are moles. My H2SO4 is going to be a similar story. So the H2SO4 as one component is the 0.0125. The 2H plus is going to be equal to the 0.025 because we have 2 of them. But that SO4 2 minus would be equal to 0.0125 moles. Okay. Now I have mixed a finite amount of both of these together. They want to know what the concentration is. That's a moles per liter situation. So I need to look at what was the volume that I had of both of these. I had 25 mils of both that I added together. And that gives me 50 milliliters total, which is 0.5 liters. If my math is right, let's make sure. Because my math sucks. I will freely admit that. My math sucks. It was 0.05, not 5. Okay. Order of magnitude off is a problem. 0.05 liters. So I take And they asked about that sulfate ion. So I take my SO4, I divide that by the 0.05 liters, and I get 0.25 more. Okay, so that's my concentration of the sulfate ions if they were all in solution. All right, sweet. Let's look at question 12. Consider the reaction of sulfuric acid and barium hydroxide to produce barium sulfate in water. If you were to remove the water from this final solution and produce water vapor from it, what would the volume of the water be at STP if the only source of water was this solution, the solutions used here? Well, from looking at this, I can see that my 0.0125, sorry, wrong number, I apologize, my 0.025 moles of OH minus and the same amount of the H plus. So I'm not going to do the calculation twice, even though they're exactly the same. 1 mole of OH minus is in 1 mole of H2O. Okay? So that means I get 0.025 moles of H2O. If we remove that, produce water vapor, that tells me how many moles I have. Okay? If I want to know what the volume of the water is, volume for the H2O, and I've taken this and made it a gas, then I'm looking at a situation where I need to use PV equals nRT. Because I know the number of moles. I know what R is. It's a constant. I know what the temperature is because it's a standard temperature of pressure. And that means I also know what the pressure is. So I can solve for the volume. And that's going to be equal to nRT over P. Now, N is that number that I just calculated, that 0.025 moles. I'm going to divide that by the standard pressure, which is 1 atmosphere. You are expected to know that. The standard, or the R, is 0.0821 liters atmospheres per mole Kelvin. And then the temperature, standard temperature, is 273.15 Kelvin. Okay. You need to know that for gases, that's STP, 273.15 and 1 atmosphere. We will talk about different things later, okay? But remember that that's what it is for gases. So I have my 0.025, I multiply that by my 0.0821, and then I multiply that by 273.15, and I don't need to divide by the 1 because I already have that. And that tells me that I have 0.56 liters is the volume that it would occupy. Okay? So that's what we're looking at there. Last question. Consider that reaction again. Can you, at this time in your chemical career, determine how much sulfate is actually in the solution? All right. I said that sulfate was insoluble. Does that mean that there's absolutely no soluble sulfate in this solution? And that's a question, because right now, I don't know. I have no way of knowing that. I've been told that it's insoluble, so I think that it's all crashed out, and that would tell me that there's none left in that solution. Now, we will get to this, and we will be able to calculate that later, but we haven't talked about how we do that yet, okay? So right now, my answer would be none, okay? Questions, comments, problems, concerns. If I have any, I would love to hear about them. Now, I'm going to stop this video now, and then we will set up for the next part, and then I will be back with you. So I will stop sharing and then I will stop recording and I will be back soon.